Okay, we'll pick up here with question G, and question G is a logarithmic equation, and you have two logarithms on the left side, log base 3 of x plus log base 3 of 2x minus 5, and you can combine those into a single logarithm multiplying the two arguments. So that's all x times 2x minus 5. So log base 3 of x times 2x minus 5 is 2x squared minus 5x. Then you can convert that to the exponential equivalent by bringing the 1 over here to the exponent and eliminating the log and taking the argument 2x squared minus 5x and putting on the right side of the equation. And 3 to the first is 3, so I subtract 3 from both sides of the equation. That gives me 0 is equal to 2x squared minus 5x minus 3. And I just swapped sides here for no reason other than I wanted to have my variables on the left side. Well, 2x squared minus 5x minus 3 factors very easily to 2x plus 1 times x minus 3. And that gives our possible solutions as x equals negative 1/2 from this factor and x equals 3 from this factor. Now you need to do no more than just substitute the negative 1/2 into this logarithm to see that log base 3 of negative 1/2 is undefined, so it is not a solution. So x equals 3 is the only real solution. Confirming that, we put 3 in for x here. Log base 3 of 3 is 1. And we put 3 here for x. 2 times 3 is 6. 6 minus 5 is 1. And the logarithm of with any base of 1 is 0. So 1 plus 0 is 1. So that solution checks. Alright, now here's another logarithmic equation. We have two logarithms on the left side, and combining those using the power property, because this is an addition, we have x plus 4 times x minus 5. Here's x plus 4. We multiply that times x minus, no, not x minus 5, x minus 4. X plus 4 times x minus 4 is the difference of two squares, x squared minus 16. So we have log base 3 of x squared minus 16 on the left side and log base 3 of x plus 14 on the right side. Well, we can drop the logarithms using the uniqueness property of logarithms, and that will give us x squared minus 16 equals x plus 14. Now, by the way, this base could have been anything. It doesn't matter. It doesn't affect the outcome here because we combined these and we used the uniqueness property to just eliminate the logarithms. So when I subtract x and 14 from both sides of this equation, I get x squared minus x minus 30. And when I factor that, I have x plus 5 times x minus 6. And so my possible solutions are x equals negative 5 and x equals positive 6. But when you substitute the negative 5 in to either of these two logarithms on the left, you have negative 5 plus 4 is equal to negative 1, and a logarithm with any base of negative 1 is undefined. So 6 is the only real solution. If you put 6 here, you get 10. If you put 6 here, you get 2. And log base 3 of 10 times 2 is 20. If you put 6, so this is log base 3 of 20. If you put 6 here, you get 6 plus 14 is 20. So you have log base 3 of 20 on this side as well. And whatever that number is, that is an equality, and so that solution checks. Okay, now another logarithmic equation here. And this one is going to have a negative solution. So we have natural logarithm of 3 minus x equals natural logarithm of x plus 5 plus natural logarithm of x plus 6. On the right side this time we combine our logarithms using the product property, and so x plus 5 times x plus 6 is x squared plus 11x plus 30. And you can drop the logarithms now using the uniqueness property of logarithms, So we have 3 minus x is equal to x squared plus 11x plus 30. And when I add x and subtract 3 from both sides of the equation, I have 0 is equal to x squared plus 12x plus 27. And when you factor that, that's x plus 3 and x plus 9. So your two possible solutions are negative 3 and negative 9. Well, if you take the logarithm of negative 9 plus 5, you get the logarithm of negative 4, and that is undefined. None of the other logarithms are defined for negative 9 either. But if you put negative 3 into this equation, 3 minus a negative 3 is 3 plus 3, which is 6, natural logarithm of 6. Negative 3 plus 5 is 2. Negative 3 plus 6 is 3. You combine these two, and you have the natural log of 2 times 3, which is 6. So negative 3 is a solution. Now, why or how can you have a negative solution to a logarithm equation? Well, it's because of this. This red graph is the natural log of x plus 5 plus the natural log of x plus 6. This blue graph, this function right here is natural log of 3 minus x. And right here, they intersect when x is negative 3. So it's because this logarithm here, natural log of 3 minus x, has been reflected across the y-axis. So a lot of its values are over here in the negative area. So that's why you can have a negative solution. All right, next we have another logarithm, log base 10, because it doesn't indicate the base, that means it's the common logarithm. So we have log base 10 of 7x minus 5 equals 2. We rewrite this in exponential form by bringing the 2 over as the exponent to the 10, even though it's not shown. We know it's there. So that's the exponent that's the base that has the exponent of 2, and the argument 7x minus 5 comes over to the right side. 10 squared is 100. 100 plus 5 is 105. 105 is equal to 7x, and 105 divided by 7 is 15. So the solution to this equation is 15. Now, question K is a little bit tricky. You once again write both sides of the equation with the same base, and e to the 0 is 1. So we have e to the 3x minus 2 here on the left side, but we have e to the 0 now on the right side. We equate the exponents, so we have 3x minus 2 is equal to 0. 3x minus 2 is equal to 0. And we add 2 to both sides and then divide both sides by 3, so we have x is equal to 2/3. 3 times 2/3 is 2, and 2 minus 2 is 0, and e to the 0 is 1. So that solution checks, even though it's an exponential equation, and we don't really need to check. I just felt like it, so I did. Okay, now we have some application, that is word problems with exponential functions. And so we have a function w of t. It's a function of time that gives the number of cases of pertussis. By the way, the informal name for pertussis is whooping cough, if you've ever heard of that. And it was eliminated, we thought, for a while, but now it's coming back. So this gives the number of cases, and that's worldwide, since 1980. Well, 1990, we're asked how many there were in 1990. Well, 1990 is 10 years after 1980, so we put 10 into the exponent here. 10, the number of years, we put 10 into the exponent here. And when you run that through your calculator, you should get 3,830, I think it's 6.6 something greater than 5, so I rounded up to 3,837. Or it may have been something 3,837 point something less than 5, and I rounded down. Technically, when we're talking about how many people, you should always round up regardless of what is to the right of the decimal. Now, 2000, the year 2000 is 20 years after 1980, so we put 20 in there, and you have your answer here, the solution here, 8,336. And 2010 is 30 years after 1980, so we put a 30 in the exponent, and we get 20,349. And those are all, as it says here, rounded to the nearest whole number. Now, if the trend continues, we want to know what year, during what year will the number of cases reach 100,000? Well, to determine that, this is the W of t. This is 100,000, so we put 100,000 in for W of t to determine what t is going to be. Well, we need to uncover the base in order to solve this exponential equation, in order to take the logarithm of both sides. So I divide both sides, 100,000, by 1665.945, 1665.945. Divide both sides of the equation by that. And so that's what you have on the left here. And that cancels this out multiplicatively, so that uncovers this base. Then you take the natural logarithm. You could use the common logarithm, but I like the natural logarithm. You take the natural logarithm of both sides here, and whatever this big nasty thing is, it's just a number. So that means we can divide it in a few minutes by this natural log of 1.07, because we take the t and we bring it around front. We use the power property to bring this around front. Now we just have t times some number. Remember, these logarithms are just numbers. And we divide both sides of the equation by that, and this big nastiness turns into approximately 49. So approximately 49 years after 1980, about 49 years, we will theoretically have 100,000 cases of pertussis or whooping cough. If the trend continues, you add 49 to 1980, and that's the year 2029. All right, next we have a famous application, actually, using carbon-14 dating. The decay rate, or the decay factor, for carbon-14 is negative 0.00012. You sometimes see a 1 here at the end, but that's more precision than we really need. So I just rounded it to negative 0.00012. And so this is the formula for age using carbon-14. The p sub 0 is the initial amount that you start with. The p of t is the amount that you're left with after a certain time. So in 1988, a 300 milligram sample of the Shroud of Turin was taken, and it was found to have 92% of its carbon-14 remaining. So that's the amount after time, or at time t, 0.92. We always have to convert a percent into a decimal to make calculations. So this is 0.92 on the left side, and that uncovers this base, because what we have here is 100%, which is just 1. No need to write that. And so we have 0.92 is equal to e raised to the negative 0.00012t. We take the natural log of both sides of this equation, and the natural log of e are inverse operations, so they cancel each other out. And so we have the natural log of 0.92 is equal to negative 0.00012t. And then we divide both sides of the equation by a negative 0.00012, and that gives us 695. So the Shroud of Turin was about 695 years old in 1988.